With fossil fuels nearing their end, a new era is dawning. It's time for solar fuels to shine. For decades, our reliance on fossil fuels has propelled economies, but has also accelerated climate change. Rising carbon dioxide levels from the use of coal, oil, and gas have pushed our planet towards a critical tipping point. In the early 2020s, atmospheric CO2 levels surpassed 420 parts per million, a critical threshold considered a dangerous tipping point for our climate. And these levels will continue to rise, with increasing industrialization to meet growing demands for energy and goods. Exceeding the atmospheric CO2 limit has profound implications for our planet, triggering extreme weather events, intensified wildfires, accelerated ice melt, rising sea levels, and catastrophic biodiversity loss. Our ecosystems and communities around the globe are already experiencing the devastating impacts of this imbalance. But there is hope. Achieving net zero emissions can help stabilize our climate, restore balance, and save our planet. This means drastically reducing carbon emissions and removing excess CO2 from the atmosphere, ensuring no further accumulation of greenhouse gases in our atmosphere. Renewable energy sources such as solar, wind, and hydropower offer significant environmental benefits, reducing greenhouse gas emissions and improving air quality compared to fossil fuels. Among them, solar energy stands out as one of the most promising options, especially here in Australia, which receives more solar energy than any other continent on Earth. However, solar energy is intermittent. It only works when the sun is shining. To overcome this, we need ways to store that energy. While batteries can store solar power, they have limitations, especially when it comes to long-distance transport, long-duration storage, and meeting large-scale energy demands. Another solution is to store solar energy in chemical form, a concept known as solar to X. This refers to technologies that convert solar energy into a range of valuable products beyond just electricity, such as fuels, chemicals, or energy carriers like hydrogen, ammonia, and methanol. In other words, X represents the many useful outputs that solar energy can be transformed into, enabling clean energy storage, transport, and use across different sectors. Many researchers have explored hydrogen as an energy carrier, but hydrogen gas has a low energy density and requires high pressure or cryogenic temperatures for storage, making transportation costly and challenging. A promising alternative is liquid fuels like methanol. With the same volume, methanol can store up to 18 times more energy than hydrogen gas under standard conditions. That makes green methanol a practical and efficient solution for clean energy transport, industrial use, and global decarbonization. Here at UNSW, we have developed a system to help close the carbon loop. One example is converting CO2 into methanol, creating green methanol as a sustainable fuel for the future. We call the system SHINE 3.0, which stands for Solar Harvesting for Integrated New Energy to produce green methanol. Traditionally, methanol is produced from syngas, which was initially produced from natural gas through steam methane reforming, a process that operates at extremely high temperatures, up to 950 degrees Celsius, and pressures of up to 30 bar. This method comes with a heavy greenhouse footprint, contributing significantly to global CO2 emissions. In SHINE technology, only water and carbon dioxide are used as raw materials. CO2 can be captured directly from the atmosphere using carbon capture technologies, or from point source pollution like coal-fired power plants or factory smokestack. SHINE combines two key processes. First, where solar energy is used to split water into hydrogen and oxygen. Here, hydrogen referred as green hydrogen. The second process is the methanol synthesis step, where hydrogen reacts with carbon dioxide to form methanol. Importantly, SHINE is designed as a continuous system, enabling efficient, uninterrupted production of green methanol using nothing but sunlight, water, and CO2. As the first step in SHINE, the water splitting process is carried out in an electrolyzer, operating at much lower temperatures and pressures than traditional steam methane reforming, which again can reach up to 950 degrees Celsius and 30 bar. This process happens across two electrodes. Oxygen gas is released at the anode, and hydrogen gas is produced at the cathode. Today's commercial electrolyzers often rely on expensive and scarce noble metals such as iridium and platinum. At UNSW School of Chemical Engineering, researchers in the Particles and Catalysis Research Group and the ARC Training Center for the Global Hydrogen Economy are developing new electrode materials aiming to make hydrogen production more affordable and sustainable. In SHINE, we power our electrolyzer with solar energy from photovoltaic panels, producing what's known as green hydrogen. Hydrogen is categorized by color based on how it's made and its carbon footprint. Gray hydrogen is made from natural gas, releasing CO2 into the air. The hydrogen used in traditional methanol synthesis via steam methane reforming is a typical example of grey hydrogen. Blue hydrogen also comes from natural gas, but includes carbon captured to reduce emissions. Green hydrogen, like the one we produce, is made through water electrolysis, powered by renewables with no direct CO2 emissions. There are several types of electrolyzers: alkaline, proton exchange membrane (PEM), and anion exchange membrane (AEM), each with unique advantages. In Shine, we use an AEM electrolyzer. It uses an alkaline environment and a special membrane that selectively allows negatively charged ions like OH to pass through. This design offers a compact, cost-effective, and durable alternative to conventional electrolyzers, combining the advantages of both alkaline and PEM systems. The hydrogen produced from the electrolyzer at low pressure is mixed with CO2 gases. The gases are pre-mixed at a 3:1 ratio of hydrogen to carbon dioxide and is stored at low pressure. The pre-mixed gas is then compressed to 100 bars and fed into the Shine reactor chamber. By compressing, we can store much more gas in the same volume. This is based on a basic principle of gas behavior. At constant temperature and volume, increasing the pressure increases the number of gas molecules that can be stored. So, higher pressure means more hydrogen without needing a bigger tank. In the Shine reactor, the Fresnel lens is used to concentrate sunlight to a fixed, small heat-receiving area, allowing more efficient heating and lowering heat loss. The Fresnel lens can provide additional heating required to bring the temperature for a reaction to proceed, where a fluidized sand bath is used to distribute heat evenly, maintaining a uniform and stable reaction temperature. This solar-driven heating method is highly efficient, relying entirely on sunlight and eliminating the need for fossil fuels, traditionally used to heat reactors in industrial processes. In the methanol synthesis process, carbon dioxide and hydrogen molecules must gain enough energy to overcome an energy barrier, known as activation energy, before they can react. To make this process more efficient, we use a catalyst composed of copper, zinc, and alumina. This catalyst is made up of solid particles with a large surface area, providing plenty of active sites for the reaction to take place. By lowering the activation energy, the catalyst allows the reaction to proceed more easily and at a faster rate. This setup is known as a plug-flow reactor with a fixed bed catalyst configuration, where the reactant gases flow continuously through a packed bed of catalyst particles, ensuring efficient contact and conversion. After the reaction, the produced methanol remains in the gas phase because the reactor operates at temperatures higher than methanol's boiling point. It exits the reactor as part of a gas mixture that includes unreacted CO2 hydrogen and water vapor. To separate out the methanol, the mixture is cooled down and the pressure is reduced, causing methanol and water to condense. The condensed methanol can then be separated and further purified to meet industrial-grade standards via a separation process, such as distillation. And since this entire process is powered by renewable solar energy, we're producing green methanol, a sustainable liquid fuel made from carbon dioxide, water, and sunlight. At Shine, safety is our top priority. We've integrated multiple layers of control systems and interlocks to ensure safe and reliable operation at every stage of the process. From gas flow and pressure monitoring to automated emergency shutoff mechanisms, each component is designed with safety in mind. These built-in safeguards allow Shine to operate autonomously while protecting both people and equipment. Engineers play a central role in advancing renewable energy systems through efforts such as process design and optimization, catalyst development, design of chemical reactions, process safety and control, and techno-economic and life cycle assessment. At UNSW Chemical Engineering, we are shaping the next generation of engineers to tackle the defining challenges of the 21st century, from sustainable energy and clean water to food security, resource recovery, and advanced pharmaceuticals. Our students and researchers are equipped with the skills, tools, and mindset to innovate at the intersection of science, technology, and society. Driven by purpose and powered by collaboration, UNSW Chemical Engineering is leading the transformation towards a more sustainable and resilient future.